Hi, in this video, I'll be going through what are Euclidean domains. So first, before we define Euclidean domain, we need to define what is a norm on an integral domain. So, a norm is a function from the integral domain R to natural numbers, or you can just think the positive integers including 0, where the norm of 0 must be 0. So you can see it's a fairly weak notion, and it's possible for the integral domain to have several different norms. But what makes now an integral domain a Euclidean domain is if it possesses the division algorithm, in a sense that if there's a norm on N, on R, such that any two elements A and B of R, there exists a Q and R such that this relation holds, where A equals to QB plus R, and the norm of R has to be strictly less than the norm of B, or R equals to 0. Then the elements Q is called the quotient and R is the remainder. And you can see now how this looks like your standard division algorithm or Euclidean algorithm, where R is less than B, because if now R is replaced by Z, then of course the function, you can just use the identity and you're done. So the importance of the division algorithm on this integral domain allows for us now to successively divide, and we can now write them in terms of quotient and remainders. And this gives us a way to produce a decreasing sequence of non-negative integers, but because we are working in positive Z, by the well-ordering principle, it must stop somewhere. And one thing to note is, because this function is any function, it may not be injective or anything, there's no guarantee that the elements are unique. So you can choose different R's as long as they satisfy this norm condition. And so some examples of Euclidean domains are any field, because they can use a norm satisfying the condition where NA equals to 0. And that's because for every A and B, there will always be an element known as A times B inverse, such as this relation holds. So every norm is 0. And the integers Z are a Euclidean domain with norm given by this in the usual sense. So it's just the absolute value of A. And another example is the polynomial rings, and it is a Euclidean domain, and the norm can be given by the degree of the leading coefficient. And the division algorithm for polynomial is just the normal long division of polynomials that you have done with. And you can now see actually why we can do the long division for polynomials now. It's because we can do the division algorithm on it. So some propositions that we will now prove is that every ideal in the Euclidean domain is principal. More precisely, if I is a non-zero ideal in the Euclidean domain R, then I is generated by a single element, and this single element is notated as D, is of minimum norm in I. So if I is a zero ideal, then there's nothing to prove. So let I not be, so suppose I is a non-zero ideal already, then you let D be any non-zero element of I of minimum norm, and this exists because this set is well ordered by using the well ordering principle of integers. So clearly the cyclic group generated by D is a subset of I, and since D is an element of I, and to show the reverse inclusion, suppose there is an A, an element of I, and we can use the division algorithm to write A as the following. Then you see that R equals to A minus QD, and since A and QD are both in the ideal, R will also be an element of the ideal. But this contradicts the minimality of D, which is supposed to be the minimum norm, and so R must be 0. And thus, A must equals to a multiple of D, and so A lies in the group generated by D. This shows that I equals to D, the group generated by D. Hence, I is principal. We can let now R equals to the polynomial rings with integer coefficients. We can see that the ideal 2x is not principal. And so it follows that the ring of polynomials with integer coefficient is not a Euclidean domain. But once you know the integers come from a few, or then it can be a Euclidean domain. So the rational polynomials are a Euclidean domain. Now with the Euclidean domain idea, you are able to use division. And so we can say that A is a multiple of B, and we can define it. And we define the multiple to be there exists an element in X such that A equals to Bx. In other words, you can also say B divides A. And with the idea of divisor, now we can come up with the greatest common divisor. And we can now define it to be such that D divides A and D divides B if and only if. So the greatest common divisor must divide both A and B already. And if any other divisors divide A and B, then D prime must divide D. So that means any other divisor must be less than D, in a sense of less than. But it's not really the word less than, but now we use divisibility to get the relation. So D prime divides A and D prime divides B, then D prime divides D. One thing to take note, if it's B divides A, then the ideal generated by A is a subset of the ideal generated by B. And so we can translate the idea of common divisor using this notion of where division and a subset of ideals to create a language for the common divisor, the greatest common divisor, in terms of ideals, where I is like an ideal generated by A and B, and D is the common divisor. Then I must be contained in the principal ideal of D, and D prime is any other principal ideal containing I, then D must be a subset of D prime. And because it's the greatest, if it exists, then it is unique. So a proposition for you to note is, if A and B are non-zero elements in a commutative ring, such that the ideal generated by A and B is a principal one, then D is the common divisor of A and B. I'll leave you to verify that for yourself, and the solution is in the textbook. So we'll move on. In the next proposition, it says that now R is an integral domain, and you have two elements D and D prime of R generating the same principal ideal. Then D prime must equals to U times D, where U is some unit. And we say now that D and D prime are associates. In particular, if D and D prime are both the greatest divisor, then d equals to ud for some unit. So now you can see that in a general integral domain where the norms could be anything, then d and d prime may not be the same, but they are associates to each other. They are related by some unit. So we suppose that d and d prime are non-zero first. Then d being an element of d prime, there must exist some x such that d equals to xd prime. But we also know d prime is an element of the ideal generated by d, and so there is some y such that d prime equals to yd. And so now d equals to xyd. And so when you bring over and then distributive law, we get that d equals to times 1 minus xy equals to 0. Since this is an integral domain and this is non-zero, cancellation laws holds. And so 1 equals to xy. And this means that x and y are units. This proves the first exertion. And the second exertion just follows, since any two GCDs generate the same principal ideal from proposition 2. Now, we end this section with now a criterion to prove when an integral domain is not a Euclidean one. For any integral domain, then we can denote the collection of the unit elements with 0 as the following: r tilde. And we say that an element is a universal side divisor if it lies in r minus r tilde, so in the complement of r tilde. And that for every element in R, there is some z such that u divides x minus z. So we take note now again. We are saying that u being in the complement of R tilde is known as a universal side divisor. So u being an element of R tilde means there is not a unit, but it's a universal side divisor if every x there is some z in the units part such that u divides x minus z. And it's really a weakening of the Euclidean condition. And so now we can come up with a proposition with this, is that if we let R be an integral domain that is not a field, if R is a Euclidean domain, then that it will be a universal side divisor. And this is easy to prove because suppose R is a Euclidean with some norm, then we let u be an element of R minus R tilde, which will be non-empty since R is not a field, and we let u be of minimal norm. Then for any x in R, we can write x equals to qu plus r, where the norm of R is less than the norm of u. And because u is of minimal norm, it means R cannot lie in R minus R tilde. And so R must lie in R tilde. And this gives an existence, because there is some, of a universal side divisor. And really, this really helps us to show that if R does not have any universal side divisor, then it cannot be Euclidean domain. And now you can use the example over here to show why this ring is not a Euclidean domain by showing that it contains no universal side divisors. This is because we already, and this is a very classic example by the way, and so we will just go through it. We have already determined that the plus minus ones are the only units in this ring, and R tilde must then be 0 plus minus 1. So suppose there is a universal side divisor, and then we just let the norm equals to a squared plus ab plus 5b squared denote the field norm on R. And because of you can factorize it and get this following, which you show that it's greater than 5. And so any non-zero, the smallest non-zero element value on n can be only 1 and 4. For the units plus minus 1 and for the elements plus minus 2. So you just take x to equals to 2. And it follows that you must divide either 2 minus 0, which is 2, or plus minus 1. 2 plus minus 1. So u is a not unit divisor of 2 or 3. So if 2 equals to alpha and beta, then 4 must equals to norm of alpha times the norm of beta. And by the following remark above, this means that alpha or beta has norm 1. So it's either plus minus 1. Hence the only divisors of 2 is plus minus 1 or plus minus 2. And similarly, the only divisors of 3 will be plus minus 1 or plus minus 3. And this really strings that u must either be plus minus 2 or plus minus 3. And if we just take x equals to 1 plus square root minus 19 over 2, then we can just check that none of x or x plus minus 1 are divisible by plus minus 2 or plus minus 3. And really, if you follow through with this example, it's been laid out to show that there is no universal side divisor. If you're still unsure, just read it again and just check with the definition of the universal side divisor. That's all for this video, and I'll catch you in the next one. Bye!